These are aerosols. Liquid and solid contaminants such as these are present in many of the gases treated in gas processing plants and refineries. These contaminants are extremely small and difficult to remove. Aerosols can cause costly fouling of sensitive equipment, rapid deactivation of expensive catalysts, and deterioration of product quality. By implementing technology that efficiently removes aerosols, these facilities could realize significant savings. Pall Corporation, the world leader in fluid clarification for the oil and gas industry, has a family of liquid gas coalescers which can remove aerosols as small as 0.01 microns from gases. The removal of these minute contaminants is necessary to maintain the performance of such processing equipment as compressors, turbines, and burners, as well as expensive catalysts and desiccants. Knockout drums, mist eliminators, and vane separators cannot efficiently remove these fine aerosols. Pall coalescers can significantly decrease maintenance costs over these traditional separators. The Pall liquid gas coalescer has definite advantages over other coalescers. Obtaining an LG coalescer from Pall ensures that you'll be getting the most efficient system available, specifically selected to match the needs of your operation. To begin with, the sizing of a coalescer is critical to its ultimate performance. An undersized coalescer results in continuous liquid reentrainment, poor liquid separation, and vulnerability to any changes in process conditions. The critical nature of coalescer sizing is demonstrated here. You can see how increasing flow to the coalescer relates to the liquid concentration in the effluent gas. Initially, flow increases do not affect the effluent quality. However, the coalescer's performance decreases very rapidly once it is challenged with too much liquid, as caused here by a high gas flow rate. In this case, the liquid carryover is more than 1,000 times greater when the flow rate is increased to just slightly above its maximum flow capacity. Therefore, it is clear that an undersized coalescer is incapable of eliminating the problems associated with changes in process conditions. In order to avoid the serious problems associated with undersizing, certain parameters must be considered when sizing a coalescer. These parameters are gas velocity through the media, annular velocity of the gas exiting the media, aerosol concentration in the inlet gas, and drainability of the coalescer. In a properly functioning coalescer, small liquid droplets called aerosols come together to form droplets both large and heavy enough to be separated from gas due to gravity. If the medium velocity is too high, the force of the velocity will begin to break up the coalesced liquids into smaller droplets. These smaller droplets are not heavy enough to be drained by gravity. Instead, sparging occurs. This results in liquids being reentrained in the gas stream. The medium velocity is a function of inlet aerosol concentration, the medium's pore structure, and the medium's surface energy. The fact that a coalescer system is designed with an acceptable medium velocity does not ensure that it is free from problems. Large coalesced droplets can still be reentrained if the velocity of the exiting gas or annular velocity is too high. Annular velocity is a function of the space between the coalescer cartridges. This top view of a coalescer assembly shows the annular space between cartridges. Adding more cartridges to the assembly decreases the annular space and increases the velocity of the exiting gas. This dramatically escalates the probability that even large coalesced droplets will be reentrained in the exiting gas, as shown here. The inlet aerosol concentration also affects the sizing of the coalescer. The higher the liquid concentration, the greater the number of cartridges required. Drainage can be improved by treating the coalescer with a chemical that lowers the surface energy of the coalescer medium. Paul treats all of its liquid gas coalescers to make them both hydrophobic and oleophobic. This prevents the liquid from wetting the filter medium and accelerates the drainage of coalesced droplets from the medium. To illustrate the effect of chemical treatment, we take a section of Paul's chemically treated coalescer medium and a section of a competitor's medium. Note how quickly the Paul medium drains the oil compared to the untreated medium. Not only does a fully saturated cartridge increase the likelihood of reentrainment, but it also will have a higher pressure drop, resulting in greater operating costs. It is also apparent that a cartridge capable of rapid draining can be put in a smaller assembly, will recover very quickly from slugs of liquid, and can better withstand fluctuations in process conditions. Here we see how chemical treating affects a coalescer operation. This is Paul's patented chemically treated coalescer. Most of the liquid drains internally. Note that liquids are only present at the bottom portion of the cartridge's outer surface. Next, under the same conditions, we test a competitor's coalescer, which does not have chemical treatment. The entire outer surface of the cartridge is saturated with the liquid. It is here that sparging occurs. At this point, the liquid is being reentrained into the exiting gas. This causes significant contamination downstream. Paul Corporation's staff of engineers and scientists evaluate all your system parameters, including the medium velocity, the annular velocity, and the inlet aerosol concentration to ensure an optimally designed coalescer system. Data are collected from your system when required to ensure the coalescer's optimum design. To find out how a Paul LG coalescer can reduce your energy consumption, improve your equipment reliability, increase catalyst and desiccant life, and decrease maintenance costs in your plant, call Paul direct at 1-800-645-6532 or contact your local Paul distributor.